Okay, so we were just commenting on a theorem analogous to what we more or less showed for Taylor series, for Laurent series, right? That essentially that we're analytic in some annulus, then we can be expressed as a Laurent series, right? So let me just remind you of what it is we said. So we have F analytic in the annulus given by following. Here, of course, remember we're possibly allowing R to go to 0, right? So we just have a punctured disk. In this case, then F can be expressed as follows. The sum from j equals 0 to infinity of a sub j times z minus z naught to the j plus the sum from j equals 1 to infinity of a sub negative j times z minus z naught to the negative j. Here, of course, we have both series converging in the annulus and converging uniformly. For any closed subannulus. Just so we have labels during the course of our proof, we'll have a little r strictly less than rho 1, which is less than or equal to the modulus of z minus z naught. Less than or equal, right, which is less than or equal to rho 2, which is less than r. Here's the important part, or a important part, with coefficients. Given by a sub j is equal to something very reminiscent of the Cauchy integral formula, but here I'm not necessarily saying that this is equal to some derivative of f evaluated at z naught. I'm just considering these integrals. Yeah. Okay, I'll come back to this during the course of the proof, but notice I'm not saying anything here about the relationships to the derivatives of f evaluated at z naught, because nothing in our assumption says that we're differentiable at z naught. That's kind of the point, right? We want to come up with a series development of some function which is perhaps not differentiable, not analytic at some point, right? Yeah?
Just a question about so the left-hand term, the sum from AJ for positive J.
This?
Yeah.
Yeah.
Didn't we show last class that those coefficients, those AJs, were given by the Taylor series coefficients?
Yeah, right. So I'm stating this in generality, right? For plus or minus j's. Okay? Okay. Good. So let's see here. C is any positively oriented simple closed curve. Lying in the annulus, having z naught on its interior. Okay. So, I mentioned this already. In order to prove this, I'm just going to we'll prove together here now that we have this stronger condition of uniform convergence on any closed subannulus. And then an argument that you'll make for the Taylor series case will apply here as well to show that it must converge pointwise on the open annulus that you're given in the theorem, the hypothesis. Okay? So, right. Here's the proof. Or an abbreviated version, at least. We'll show uniform convergence on any subannulus. Sorry, closed. Okay. And we'll leave the rest to you. Okay, so I made some offhand remark of how we'll start to do this. Right. To begin, for any z satisfying this string of inequalities, sorry, this is a strict inequality. We have representation f of z is equal to 1 over 2 pi I times the integral traversed once in the opposite, the negative orientation of this circle C1, f of zeta divided by zeta minus z d zeta plus the integral around this contour C2 traversed in the positive orientation once, f of z divided by, f of zeta divided by zeta minus z zeta. Okay. Now, let me draw you a picture to show you exactly what I mean when I talk about C1 and C2 here. Okay? So, I'll try to keep this up throughout the course of the proof. Here's our Z naught, right? And we start here's the inner radius of our initial annulus, right? Okay, and I'm trying to give myself enough space here. And here's the outer radius of my initial annulus. Okay, so what we want to do is we're going to look at some closed subannulus, right? So here we'll have say row 1, yeah, and then I want to go out to row 2. This is very quickly becoming a complicated diagram, right? Okay, now here's, wish I had brought colored chalk. Okay, so we want to construct these two contours, C1 and C2, based on the radii that we have floating around here, so that they lie in between our relevant annuli, right? So essentially, I want to go, let's see here. Yeah, I will come in between little r and row 1. And give this negative orientation. Okay, so I know this is already becoming a little cluttered, but I'm designating my curves with their orientation drawn, right? So this is C1, this curve in here. Okay, and we'll insist that this curve has, circular curve, has a radius R1. Okay? And then I want to consider a curve that lies between the circle of radius R the open circle of radius r, and the closed circle of radius rho 2. Okay? I'm going to come in this in-between layer. Okay, and I'll give that the positive orientation. This is R2. Okay, I know this, again, is confusing because we typically use dashed and solid to mean open and closed. But now I also have oriented contours flying around, right? So I want you to pay attention to these two arrows. Okay? And now I'll write down the formulae for R1 and R2, which you can probably guess, right? It's the average of the radii, rho I and little r or big R, respectively, right? Oh, sorry, I forgot one label here. This contour is Z2, right? The larger oriented contour. Okay, so we're going to refer back to this picture quite a bit over the course of this proof. Okay, where C1 is the negatively oriented circle around, or maybe I should say centered at Z naught, with radius R1 just given by little r plus rho 1 divided by 2, right? The thing that lies in between, just in the middle of those two radii. Okay? And C2, the positively oriented. Circle centered at Z naught. With radius R2 given by hopefully just what you would expect. Capital R plus rho 2 divided by 2. Okay? So I quickly want to justify this claim that I can actually represent my function in this way. I gave you a preview of how this argument goes using this annulus contour with a chunk taken out of it. Right? Okay. So this representation is a variant of Cauchy's formula. Okay? I'll draw this picture again. Not this picture, but something simpler. Let's take, again, our Z naught, and we have some point Z. Then we we take a segment of our annulus, orient it in the following way. Right? Okay, so when we integrate around this contour, let's call this gamma. Right? We have the Cauchy formula. Right? I can use the Cauchy formula because remember I assumed I was analytic inside the annulus. Right? Okay. So I take the integral along the contour gamma of zeta divided by zeta minus z d zeta. Okay? Now, all I've done to produce this contour gamma is take a chunk out of my annulus, right? Took a bite out of this donut. Move it. So what I would like to do is consider that piece separately that I removed. Okay? So let me look at this called gamma prime. Then what do we have here? Let me orient this. Okay. While what I would say about the integral of this is along gamma prime f of zeta divided by zeta minus z d zeta. This is just equal to 0, right? Because it doesn't contain the z. Yeah. Okay. So I can rejoin the parts of the whole annulus. Right? I can just push this chunk back in, right? And I'll still not contain z. To get the following, f of z plus 0, I'll write in a very pedantic fashion, gamma of, this is the same as, oops, sorry, forgot my constant up front. 1/2 by I times the contour integral along gamma plus gamma prime of f of zeta divided by zeta minus d d zeta. Okay, so when I rejoin these pieces, what happens to the line segments?
They have opposite orient. Oh, so they cancel out.
Yeah, they have opposite orientation, so they cancel one another. Okay? So the line segments plus gamma prime cancel each other. And we're left with what? Just the concentric circles of opposite orientation. Right? That's what the sum of gamma and gamma prime is. Hey, try hard to not erase this picture. Right? So, so altogether, this gives us our result, right? That f of z is just the contour integral around C1 plus the contour integral around C2. I like this argument. It's nice. It's a clever use of contours, right? Okay. So,
Is the dz or d zeta on this?
oh yeah, sorry, that's zeta. Good eyes. Thanks. Okay. So, now let's do some analysis on this sum of integrals. Right? So, one thing we know from our picture is that z lies inside C2. Right? So, which gives us that this integral is equal to J plus T sub n of z, right? This is just like when we were arguing about the Taylor series, right? Because we just have, in the case we're considering just z, we're just looking at the disk surrounding z.
T sub n was the error term?
Yeah,
Okay.
yeah, exactly. Okay. Just like the Taylor theorem. Where the error, remember we showed, by bounding the integral that this is, we we showed that this goes to 0 uniformly, as n goes to infinity. Right? I should say, of course, for this disk, okay, with a j equal to the integral along C2, reversed once in the positive orientation. Okay, just like the Taylor formula, but again, here, remember, there's no hypothesis on the differentiability of f at z naught. Right? So we can't apply the generalized Cauchy formula to this. That's okay, we'll just leave it like it is. For now. Okay. So, right. That is to say, what we get is that even though the coefficients are slightly different, we still get that the integral that we were considering, this integral around C2, is just some power series. Right? Okay, so that is to say, I'm telling you that we can make the same argument as we did for the case when we were actually working with the Taylor series for the error going to 0 for this integral around C2. Okay. So now we'll look at our second summand. Well, really I wrote it as the first one, the integral around C1. Let's see what we can say about a series development of that. Okay, so this case was analogous to the Taylor series part. Here we'll do something slightly different. Okay. So the integral around C1, and note z lies outside C1, and for zeta on C1, we can do some tricky arithmetic, right? We can look at this part of the integrand, right? I'm just taking the denominator out separately. tell me what I'm gonna do here. Something that we've done a couple times at this point. I'm going to rearrange this algebraically so that I can express it as some factor, times a geometric series. Okay, so that I can come up with a series expansion of this part of the integrand. Okay? So here's what I'll do. And it may seem like this is something you've never come up with, but once we actually start computing Laurent series for various rational functions, say, or really any functions that have poles, we'll use this same type of trick all the time. But it'll be easier to see because you're actually working with numbers most of the time. Okay, but I'll show you again now what the general procedure is. Okay, so what'll I do? I'll find a clever way to add in a 1 to the denominator. Or I'm sorry, add in a 0 to the denominator. Okay. Okay. So, and then what I'll do is I'll factor a negative 1 over z minus z naught, so that I get a 1 over 1 minus zeta minus z naught divided by z minus z naught. Okay, why is this the thing to do?
The right side, you have the R factor of that.
Yeah, I have the common factor for a geometric series, which must be less than 1. Right? Look back at our diagram. Remember I said gamma is on C1, right? And we were assuming Z is somewhere here. Yeah? So the distance from Z naught to gamma will necessarily be less than the distance from Z naught to Z. Okay? I know this might seem quite unnatural, but it comes up all the time. You'll get used to it. Okay. So, that is to say, since we have a geometric series converging, we still have this factor of negative 1 over z minus z naught out front. And then we have our expanded geometric series. Plus my error term, right? If I'm only going up to m. Z minus z naught should be m plus 1, all divided by 1 minus zeta minus z naught divided by z minus z naught. Okay. Now, formally, we're going to do the same thing. We'll plug this back in to our integral here. I'm going to use the linearity of contour contour integrals to split it up across all the terms of this sum. Okay, so plug this into integral. And what do we get? Well, you just get our expression. Is equal to the following. So I'll just write this down and then we'll talk about it a little bit. A equals 1 to n plus 1 of a sub negative j times z to the z minus, minus z naught to the negative j. Plus, just for variety of notation, so we don't get too confused, I'll use a script t here. And you'll notice that I also use the index m here instead of n. So we keep it separate from the integral along C2 that we just computed. Same concept though, this is the integral term coming from our error term. Right? Okay? Where a to the negative j is equal to negative 1 over 2 pi I times the integral along C1 traversed once in the negative orientation. Right? For j equal to 1, 2, so on and so forth. And t sub m of z is just equal to 1 over 2 pi I, again, times this contour integral around C1, once negatively oriented, and for zeta, divided by zeta minus z, times our error term, zeta minus z naught, divided by z minus z naught, raised to the m plus 1 power d zeta. Okay, so everything I've done is just formal manipulation so far, right? I've just plugged the power series into an integral and pull it apart by linearity. Okay, now, what am I going to do? I want to show my final result. Take a look back at your notes, and what is it we're trying to show? Is that we get some, yeah?
I think you do change the orientation of C1. Take care of it.
Yeah, that's we'll definitely have to do that. That's good. Right, so yeah, remember that C1 is negatively oriented, and we get all these negative signs in our coefficients. There was no such negative sign in our statement of our theorem. Well, that's okay, we'll just flip the orientation of C1 and get rid of the negative sign. Good. But there's a more pressing matter.
We have to show that Tm goes to 0.
Yeah, we have to show that this uniformly goes to 0, which we'll do as we've done several times at this point by just bounding the integral and showing that it goes to 0 and then goes to infinity independent of z. Right? So, we'll bound script T sub M of Z in modulus. Okay, well, what are some things we noticed right away? Remember, we're gamma on C1, the contour C1. We have some inequalities, right? Namely, first of which is that the modulus of zeta minus Z is greater than or equal to rho 1 minus R1. Now is where we're going to start referring heavily to our diagram again to justify all these bounds that I'm writing down. Okay? What else can we say? Well, we also know that the modulus of zeta minus Z naught is just equal to R1, right? R1 is just the radius describing this contour C1. Okay? Well, we can say a little more, right? We can also say the modulus of Z minus Z naught is greater than or equal to rho 1. This was by us insisting that Z lie in the annulus where F is analytic in the first place. Right? That's schematically, I just randomly put it somewhere in the annulus here. Okay. Okay, so that actually gives us enough information to bound the modulus of script T M of Z. This is less than or equal to, well, we just get a 1 over 2 pi from our constant out front. Times the maximum over zeta on C1 of the modulus of f of zeta times 1 over rho 1 minus R1 times R1 divided by rho 1 to the m plus 1 times 2 pi times r sub 1, the length of our contour. Yeah.
When we say that the modulus of Z minus Z naught is greater than or equal to rho 1, if it were equal to rho 1, Z would be on the same contour, or the same circle as zeta, right? Because zeta's, I'm looking at the diagram, I think this is right. Zeta's on the circle with radius rho 1.
Yeah.
Didn't we say that the zeta minus Z naught had to be strictly less than Z minus Z naught for the geometric series earlier? So it wouldn't have to be like just strictly greater than rho 1? I don't know if that matters. Because like if Z is on the same thing as zeta, then when we were doing, I think you just erased it, but when we were doing the geometric series earlier, the like, the zeta minus Z naught over Z minus Z naught, you were saying it had to be less than 1 because the zeta minus Z naught had to be less than 1.
You're right. I think you're right. Yeah, I should make this strict.
Okay.
Good, thank you. Doesn't affect the argument at this point, but it's inconsistent with what I said before.
Oh yeah, I wasn't sure if it mattered, I just wanted to...
Yeah, no, it's I'm glad you said that. That's good. Okay. Right, so we're bounded. Now as long as we can show that this goes to 0 uniformly as m becomes arbitrarily large, then we know that our error must go to 0 uniformly, right? Well, that's not so hard, right? Mainly because of this term. Entirely because of this term, right? Because rho 1 is bigger than R1. No, I'm sorry. Yeah, that's right. Row 1 is bigger than R1, right? Row 1
Yeah, okay.
is bigger than R1. Yeah. Here's row 1, here's R1.
Wait, isn't R1 so R1's the radius of C1? No.
R1's the radius of the contour between C1
Yeah.
and the.
Isn't it
No.
bigger than O1?
No, it is the radius of C1.
Wait, is it? We can-
It is the radius of C1.
Oh.
And row 1,
Yeah.
row 1 is the
Yeah,
original
yeah.
annulus bound, right? It's the smallest thing.
Okay, okay.
Okay. So we're good, right? So, as m goes to infinity. So this gives us our equality, right? Except up to what Joe was saying, switching the signs, because we flip the orientation. And so we get rid of all the negative signs on the coefficients a, negative j. Okay. The only thing left to do is to show that I gave a general formula for the coefficients, right, of both the series summations that I stated in the theorem. So in order to arrive at that conclusion, all you have to do is start at C2 and shrink down to any contour inside the annulus for the C2 coefficients. And then for the C1 coefficients, just enlarge it, become bigger up to an arbitrary contour inside the annulus. Okay. I'm not going to try to make a drawing of that or say more, but I'll just leave that open because I didn't say exactly everything. Okay, so great. The intuition is that when we're not necessarily analytic, and we are analytic in a disk, and we are analytic in some annulus around where we're not analytic, then we can use Laurent series much like we use Taylor series. That's the idea. Let me give you some credence to that idea by just stating the analogous theorem for Laurent series. Remember, we had this amazing fact that we proved to some degree about Taylor series, which said that every power series that converges in some disk, we showed why it has to be a disk, every power series that converges in some disk has to be the power series of some analytic function, or sorry, the Taylor series of some analytic function. So we can say the same thing for a pair of series that converge in this way. That is to say, if a pair of series act like a Laurent series for a function, or converge in some annulus, then they must be the Laurent series for some function in that annulus. Specifically what they sum to. Okay? I'll state this theorem, then we'll take a break, and then we'll compute some examples specifically, how to find the Laurent series of some functions, which are not analytic everywhere. Okay, so let's let themselves have the following two series. Oh, sorry, negative J. The any two series with the following properties. The first of them converges. For within this closed disk radius r. Okay. The second of these series.
You say closed.
Oh, I said closed, didn't I? I meant open. Sorry. The second of these series converges or outside the closed disk center at Z0 with radius little r. Okay. Okay, and thirdly, we insist that little r be strictly less than big R. In other words, so that we can define an annulus. Right? Okay, so any two series that satisfy these three conditions I bet you can guess what I'm going to say, or at least approximate it pretty well. Anybody?
Are the coefficients given by the formula we have? And are the Laurent series?
Yeah, that's the consequence, that the coefficients are, in fact, the coefficients you would get from the Laurent series. Yeah. Right. Then there is a function. F of z. Analytic in the annulus. Whose Laurent series is, and I think we saw this notation, but we'll start being a little fast and loose. Instead of writing this as two series, we'll just let our index go from negative infinity to positive infinity. Instead of doing this negative, multiplying the index by a negative thing. Given by this. Okay, so this is analogous to our theorem on Taylor series, right? That you have some powered series which converges in a disk, and there must be some function which has Taylor series. That is that given power series, converging in that same disk, right? Which is analytic. Same thing here. Okay, let's take a 5-minute break, and then we'll compute some examples. Yeah, great, thanks.
say when the draft was due for the?
I think he unofficially said this Friday, but he said if you had like a lot of other stuff with classes, you can just kind of get them whenever.
I think he said he has to make the due date the Friday, but he doesn't really care so long as it's in like the 14th or something, like basically when we start doing presentations.
For the draft or for the
The draft?
For the draft, he said this
you're right.
Friday.
Yeah.
But the final paper
Yeah,
was
the actual thing.
kind of loose, right?
Yeah, I think the final paper was like just by the presentations.
Yeah, that's what it sounded like.
Yeah.
How's everybody's term finishing up?
One of my professors just emailed me that I'm doing my final presentation tomorrow.
Okay.
So,
Pretty busy. I will agree with that.
Yeah. I feel just the same. I'm sure it's different on different sides.
yeah.
There's similarities, but.
The final project in electronics is just
Tough.
I have a machine learning project today that my group and I have not started. That's due the end of this week, so that'll be loads of fun.
Well, it's before the middle of the week.
Yeah,
That's a slight positive.
About 3 days.
yeah, a bunch of coding. There's some, is what it is.
so lots of coffee.
Yep.
This week, I have so much stuff this week. Tomorrow, I apparently have that presentation. I have an exam, and then I have the draft for this class due on Friday. And then the next week, I just have like nothing.
Oh, this week and the beginning of next week for me are awful.
Next week.
Yeah, I got 4 problems that's due in 2.5 days at the beginning of next week. So that'll be a lot.
Oh yeah, when's our
We
last
have one
problem?
more.
Yeah, is it alright?
agenda.
Yeah, I was wondering if you were counting that or not.
Yeah.
Okay. Yeah,
And now it's 5.
Yeah, 2 for 4.
yeah, I'll release that tonight. I'll try to make it short. Just to get some practice doing the stuff that we've been talking about in the last week. Yeah, also I just want to make sure everybody has a chance to feel like they did enough, or I don't know. It just seems like there should be one more problem set.
Probably like my favorite homework that I've done this semester. I always find like the isn't like the right term for it, but the like fancy math problems that we do in classes like this are always like so much fun to solve.
Yeah, you feel like you really accomplished something, right?
Yeah.
That's good. I'm glad to hear that. I understand there was a lot of work put into, what was it? Problem 1?
1B.
Yeah, where you had to classify the Otobi equivalence classes.
I'm not confident I got them all, but I have a lot of circles drawn.
I was telling Joe yesterday, it's mainly an exploratory thing.
Wait, how many were there in total?
I got 42.
I didn't count it.
We'll see. We'll see how many there are. When you given the restrictions, no, it should be finite. Yeah.
I got 69.
Okay.
Wait, I feel like I'm missing something. I only got 15.
Did you account for both orientations?
Oh.
Yeah.
You account for like the quiz?
Yeah, there was some weird stuff where it's like,
I drew away that.
Oh, but it can't be self-intersecting, can it?
Well, yeah, good, right?
I forget what I wrote. Did I say simple or not?
It did not say simple.
It did not say simple.
Is it closed curves traversed exactly once under paved?
Yep, I think, okay.
I wish it said simple.
Yeah, that's why it was kind of a harder problem, because it was not necessarily simple.
Simple would have been
Yeah, that would have been significantly simpler.
nicer.
Yeah.
Yeah.
Oh, I'm missing one.
Well, anyway, don't worry too much about this. As I was saying, this is mainly like an exploratory thing. I don't even have a correct answer in my mind of what it should be. So, yeah, and as for like drawing it is totally acceptable because like to really say anything, you have to talk a lot more about homotopy. So I'm expecting a bunch of drawings, basically.
Before I realized that we could do drawings, I was like 5 Wikipedia pages deep reading about like winding number or something.
yeah.
Yes, the winding number.
Yeah,
I was
I
trying
was-
to figure out what that was.
I was so lost.
Yeah. Hopefully, I think Deanna might do her final presentation on the winding.
Okay.
So that's something to maybe look forward to. Anyway, let's do some examples here with the Laurent series. Okay. What if I were to ask you to find the Laurent expansion the following function, z squared minus 2z plus 3 divided by z minus 2 in the region the modulus of z minus 1 greater than 1. Sorry. So, what do we notice right away?
You can't factor it.
Okay, so no factoring. That's good. That's a good thing to notice.
The region is unbounded.
The region's unbounded, and more specifically, the singularity of f is not contained in the region. And we're centered at 1. We're looking at.
So just
Now be careful. Let's try to actually just compute it and see what we get. Okay. So this is where this counterintuitive thing becomes really important. We want to transform a part of our function, specifically the denominator, into something that a geometric series converges to. Okay? In this region. Okay. So, for example, first, consider just our denominator on its own, still as a denominator. What we would like to do is express this as what a geometric series converges to, or some common factor. It has to be less than 1. Okay. Well, here's what we'll do. It's just like what we did in the course of both the proof of the existence of a Taylor expansion and the existence of a Laurent expansion. Okay, here's what I'll do. I'll express this as following, right? Which I factor out of the denominator a factor of z minus 1. Yeah, 1 over z minus 1 times 1 minus 1 divided by z minus 1. Now, here's where our restriction, the region that we're considering, becomes important. That's how I know what to aim at, try to get to as the common ratio of a geometric series, right? I know that the modulus of z minus 1 must be greater than the modulus of 1. So I have this factor here as what a geometric series converges to. Okay? So this is the general strategy. You'll be asked to find a Laurent expansion in some region. You have to use the information about that region to manipulate your function to have some geometric series in it related to its denominator, where it has singularities. Okay? Very tricky. But it is at least a little bit more algorithmic than some things where it's like, oh, you just have to see this. At least there's some guidelines, right? You know you're aiming at what a geometric series converges to. Okay, so then I can just write this in the following way, right? Once I recognize this as a geometric series, I have my factor out front, 1 over 1 minus z, times the sum from j equals 0 to infinity of 1 over z minus 1 to the j, right? Here's my common ratio. Of course, 1 to the j is just 1. And if I like, it may help clarify things if I just write out the first couple terms of this. Oops. Okay. Now, what to do about the numerator? I was told that there was some chatter that maybe I was assuming a little too much about comfortability with results on sequences in series. Is that true?
A lot of us had a bit of a haphazard Calc 2 experience.
Right.
Yeah,
Right.
I never actually took Calc 2.
Okay.
I took it on Khan Academy.
Yeah.
Okay.
Yeah.
Okay. Okay. So do you remember the anatomy of a power series, right? You have the coefficients, you have the indices when it goes to and from, and you have the center, right? This thing that you're subtracting from your variable, right? That's the center of your power series. So you can readjust the center of a Taylor series, say, right? Let's, so I want to readjust the center of, I'll say this in a kind of silly way, I want to readjust the center of the Taylor series for this polynomial. I want to readjust the center to the point z equals 1. So that I can come up with a Taylor expansion of this polynomial, i.e. another polynomial, right? The Taylor expansion of a polynomial is just a polynomial. And it only has finitely many non-zero terms. I want to come up with a Taylor expansion of this polynomial that has as terms powers of z minus 1. So I want to change the center from 0, right? The z minus z naught raised to a power here is z naught being equal to 0. change my center to z naught equals 1. Okay? So let's do this systematically, just to see, because maybe you have little to no experience with this. Yeah.
Oh, no,
Okay. Okay, so, what we want to do is then express z squared minus 2z plus 3 as a Taylor polynomial centered at z naught equals 1. Okay, what will I do in order to do that? Well, here's what I'll do. Actually, I guess I should use g. I call my whole function f. Here's my function. Here's its first derivative. Here's its second derivative. And just for completeness sake, I verify that all the derivatives after that are 0. Okay, then what I'll want to do is evaluate all these derivatives at z equals 1. So g of 1, what do I get here? 0, right? Oh, no. 2, yeah, that's right. Thank you. G prime of 1. This gives me 0, right? 2 minus 2. G prime of 1, 2. Okay, so now I have all the data I need to just plug into the formula for a Taylor expansion, right? So this gives me a Taylor expansion centered at 1, given by the following. I'll just write it out to be totally explicit here. I know that I'm 0 forever after the third derivative and all. Okay? So in other words, what do I get here? I computed this f of, I'm sorry, these are g's. My mistake. G, G, G. Okay, I computed g of 1 to be 2. Right, so I get a constant term 2. I computed g prime of 1 to be 0. I get 0 times z minus 1. And I computed g double prime to be 2 divided by 2 factorial is just 1. So, in other words, my original goal, remember, was to express my polynomial as a sum of powers of z minus 1. This is what I mean by changing the center of my Taylor expansion. And it just so happens that Taylor expanding a polynomial just gives you a polynomial back.
A question kind of like Calc 2-ish and like this, I guess. That thing converges to g of z for all z.
Yeah, it in fact equals it, yeah.
Yeah, is that just a property of moving polynomials?
Yeah, you can move polynomials around this way any time.
And they always are identical.
Yeah, right, that's because, so, yeah, it's kind of, not easy to see that if you just proceed strictly algebraically, but if you use Taylor's theorem, then it's obvious, right? Because it's like, okay, this is a polynomial, has a Taylor series that converges everywhere. It's just the polynomial, and you can change the center of a polynomial within the interval where you converge. If you converge everywhere, you can change the center to anywhere.
Foil that out, you can see things.
Yeah.
Yeah, right. So yeah, I didn't have to use calculus to do this, but it makes more sense if I use the system that Taylor expansion set up for us.
Was that the same result you get if you do polynomial long division?
Well, okay, so what would you be dividing here?
Never mind, yeah.
Yeah, it's slightly different.
Top over bottom.
Yeah, so we're doing a different type of operation. We're coming up with a different product and sum. So it's kind of a powerful thing if you want to rewrite polynomials in an arbitrary way. Okay, so I went to this trouble of recentering my polynomial. So what can I say now? Altogether, this tells me that the function I started with, is this right? No, it's not right. Z squared minus 2z plus 3 divided by z minus 2 is equal to I'll take the polynomial that I recentered on my numerator to z minus 1 squared plus 2, and I'll multiply it by the expression I came up with for a series that represents the denominator, right? Due to my geometric series expansion. Now it becomes a little more apparent why I insisted on rewriting this as centered at z minus 1, right? Because I'll get cancellations when I distribute to this geometric series. Okay, so specifically, let me write this out. So first I'll just take this term and multiply it through all the geometric series. What do I get from that? I get z minus 1 plus 1 plus 1 over z minus 1 plus 1 over z minus 1 squared plus, now I'll distribute the 2 everywhere here. Okay. 2 over z minus 1 plus 2 over z minus 1 squared 2 over z minus 1 cubed. Okay, now we're almost done here. We get z minus 1 plus 1 plus 3 divided by z minus 1 to the j. Right, because I get 1 over z minus 1 here and a 2 over z minus 1 here. I can pair up all the summands with the common denominator, and in that case the numerator adds up to 3 each time. And out front I just have these two terms that don't pair with any of these terms, with 2 in the denominator. Now why do I bother keeping these separate? Well, that just kind of highlights the original series expansion that we proved just recently. That the Laurent expansions are expressed as power series centered at z minus 1. Here are the non-negative powers, 1 and 0. And for any larger non-negative power, I just have a coefficient of 0. Okay? And then here, for all the negative powers, I have just a coefficient of 3. Okay.
So that's technically the z minus 1 plus 1. Which are kind of like, you can think of them as like the first two terms of the Taylor series. And then the other part is the negative exponents.
Yep, that's exactly right.
I think that's why you wrote it as z minus 1 plus 1.
That's exactly why I wrote it that way.
Yeah.
Good. Let's not forget that this series expansion applies in this region. Right? I just wanted to reiterate that so we didn't lose sight of. Don't be fooled into thinking, oh, this series converges to our function everywhere. Well, clearly that's not true because we're singular at 2, which is not in this region. But it converges most everywhere outside this disk. Yeah. Okay, good. So just to highlight that last comment a little bit further, let us look at how a Laurent series expansion might change when we change the region that we're considering. Okay, so find the Laurent series for 1 over z minus 1 times z minus 2 in the following regions. Okay, region A. Let's just look at the open disk of radius 1. Region B. Let's consider the annulus, open annulus between 1 and 2. And C. Consider the complement of the closed disk centered at 0 of radius 2. Okay, so what should be our first step here? If we
Partial fraction.
Yeah. We want to replicate the type of thing we did in our last example. We would like to put ourselves in a situation where we have a single linear factor in our denominator. So we can do that twice over by applying partial fractions here. Okay? So first, for all regions, apply partial fractions. This is not a particularly hard partial fraction problem. I got the following. Okay. So now, well, we're actually, we have a bit of luck here, right? We computed a geometric series that holds for this in a certain region. Maybe we'll be able to use that along the way. But for now, let's just start at A, right, where we're looking at the disk centered at 0, radius 1, open. So right away, what can we say about the comparison with the geometric series that we found converging in our last example compared with part A?
The other one was greater than 1.
It doesn't apply in this region, right? The last geometric series that we expanded this to does not apply in region A. No? Okay. So let's start from scratch then. Okay. Okay. So for the modulus of z strictly less than 1, how can we arrange it so our first summand is a geometric series, or is something that a geometric series converges to, I should say?
You pick a point to center at 0.
Well, so we don't have to recenter any polynomials because we're in luck, right? Our numerators are just
in
1.
the sense that the way we found, like we wrote the bottom of the last example as so like 1 over z minus 2 into 1 over z minus 1 minus 1.
Yeah, right. So in this region, what expression can we get involving z in the denominator that is 1 minus something that's less than 1 is basically what we need. Okay, so when I say 1 minus something less than 1, I mean something less than 1 that depends on z. Right? So in other words, I want to transform this 2 into a 1 somehow.
Would it be 1 over z times 1 over 1 minus z?
Okay, I think there's something simpler to do, right? We can just factor out a half, negative half, right? And then just have 1 over z minus 2, which is equivalent to what you said, right?
I don't think yours would run, Joe, because you have 1 over z, but z is less than 1, so that you could.
Oh yeah, it's because of
If you do, what we did last time, like the factoring out the 1 over z or like some kind of business doesn't work in this one since you get a factor greater than 1.
Yeah, right. So the thing that depends on z, which has to be less than 1, should have z in the numerator, depending on this constant 2, right? Okay. Okay. Good. So I just get negative 1/2. I guess, of course, I should say, since the modulus of z is strictly less than 1, z divided by 2 will be less than 1 in modulus. So what do we get here? Z over 2 to the j, or if you like, just negative sum from j equals 0 to infinity of z to the j divided by 2 to the j plus 1. Yeah. Okay. Okay, so, and what about for 1 over z minus 1? What can we say here? This is a certain capacity kind of simple, right? We know about z in this region.
Less than 1.
That is less than 1 on its own.
So we just factor out the negative sign.
Yeah, so we just pull the negative out. Raised to the j. Now, okay. So altogether, I want to come up with the Laurent series of this function. I'll just take the series expansion I got for 1 over z minus 2. And subtract what I got for the series expansion of 1 over z minus 1, which is negative, and it has a negative sign. Okay, so let's do a little series arithmetic, and what do I get? To the j, sorry. Okay, so I don't know, sometimes it's somewhat illuminating to just expand out a couple terms, just to see if you get any negative terms, or any positive terms, or both. So this kind of makes sense. This is just a Taylor series inside the disk, because all the singularities lie outside the open disk, right? So we don't have any negative powers in the Laurent expansion. Okay, so that's 315. I hate to say it, but you know, we might not get everywhere I want to get by the end of next Tuesday, but we're gonna keep trying. Okay? So yeah, I'll release some homework assignment tonight. And like I said, it should be easier. And that'll be due next Wednesday, the last day of class.
Mark texted me and said that Israel had a suggestion to like fix our circuit.
What's up?
Apparently Israel had a suggestion to
Yes,
fix
yes.
our circuit. I didn't know that Israel had to do a circuit once.
Like, I really didn't even.
That's impressive.
I go up there and like start like drawing things on the board. You move to under this project, and instead of looking at anybody, So this blows up, right? It's like what? And then you can't really use big welding, and you start tapping.
Oh, there's no name on this, is this yours?
Mine is in your door.
Oh, you already put it in the door, okay, so I think this must be front.
I would say I have mine.
Yeah, you're still prepared.
Yeah.
Is it like
Yeah,
name
see-
on the back or something maybe?
No, that's okay.
Have a good one.
See you.
Do you want me to go staple this and give it?
I have a stapler
Okay.
in my office.
Okay.
I'll make sure to not get them too messed up.
I wasn't able to get to 5A in time, but
That's okay.
oh well.
See, that problem set, I think, ended up being longer than I anticipated, or